Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. Today we're having a look at 14.7 number 41, which is something like a classic multivariable optimization problem. And let me encourage you to, if you haven't done it yet in this course, to start using Matlab or Mathematica, because this is really about the point in the course where those computer algebra systems greatly simplify the amount of work and the kind of work, so it kind of removes the computational drudgery from the problem and frees up our minds for the higher level thinking. So let's go ahead and interpret the problem. And so here we want to use optimization to find the points of minimum distance, because that's what closest to really means. Closest to means we've minimized the distance between the point and the cone. Alright, so to develop the problem, we need to make our plan. And the plans for a lot of these multivariable optimization problems end up to be very similar. So first we want to write down and identify what's called the objective function. And here, since we're minimizing a distance, we use the distance formula. And in these multivariable optimization problems, we're usually concerned with two main equations. One of the equations describes the objective function, and the other equation is the constraint function, and we want to identify the constraint function. Once we have the objective function and the constraint function, then we can use the constraint function to reduce the objective function to two variables. And once we have the objective function in two variables, we compute partial f, and assuming that we're calling the objective function f, partial x equals 0, partial f, partial y equals 0. We solve, and this gives us critical points. And now we simply need to test the critical points one by one to find the minimum. And one thing that's going to occur to us as we go is, rather than minimizing the distance, because the distance formula has a square root operation in it, and when you take the derivatives of things with square roots you get more complicated answers, we're going to minimize the square of the distance and make the square of the distance our objective function. Because the distance formula basically says the distance between this point and any point, just call it x, y, z, is going to be 4 minus x squared plus 3 minus y squared plus z minus 0 squared. So the square root and the sum of the squares of the differences is the common distance formula. But what if we let our objective function f of x, y, z equal to d squared? Now we're essentially, we no longer have to handle the square root in all of our computations. Use the constraint. Well, first we need to identify the constraint, and the constraint is that whatever point we come up with, it has to be on the cone. So the constraint is the equation of the cone, namely z squared is equal to x squared plus y squared. So that's our constraint. So we can substitute in z squared here And now write f of x, y is going to be 4 minus x squared plus 3 minus y. And you got to be careful, those squares have a way of jumping from the outside to the inside of the parentheses, and that's like a whole monkey wrench into works. Alright, now the z squared, we substitute in, z squared equals x squared plus y squared. And now we have the objective function reduced to two variables having used the constraint function. And we could slog this out by pencil and paper like we did in the video on number 30, but there's no need to. So from here I'm going to show you how we can complete this optimization problem using Matlab to do the heavy lifting. Okay, so the computer is running Matlab, and the first command that we need to execute is we need to give it a sims xy real. And what this command does is it informs Matlab that we're going to treat x and y as real variables. And now we can define our function of x and y that we're going to optimize as equal to 4 minus x squared plus 3 minus y squared, and then plus x squared plus y squared. And so that, oops, take a little care here, somehow it doesn't like, I see what it doesn't like. It doesn't like that we use the function notation in the usual way there. It just prefers to define functions like that. Alright, so now we have the function defined according to the Matlab syntax, which it gave us some feedback about when we messed it up. And now we can say, I'm going to call it df dx. So that's just the notation I'm using for the partial derivative of f with respect to x. And the Matlab diff command differentiates a function with respect to a variable. And now use the same thing to define df dy as the partial derivative of f with respect to y. And now we want to use the solve command, and you always need to input the outputs of the solve command in alphabetical order, and then we can go ahead and the arguments of the solve command are the things that we want to make sure equal to 0. So that would be df, dx, and dy, dx. If this syntax seems unfamiliar to you, perhaps you can check some of our Matlab practice videos where we just concentrate on using Matlab to work some example problems in Calculus 3. And oops, we did dy dx instead of we wanted df dy. Matlab once again reminding us that our syntax has been imperfect. And make the window a little bigger. And it tells us that the solution to the two equations and two unknowns is x equals 2 and y equals 3/2. So that is our critical point. And since we only have one, of course it's going to be the minimum. So we can plug that value of x and y back into our original distance formula and compute that closest distance, but the point with the closest distance is x equals 2, y equals 3/2. And then if we wanted to do a double check, we could use Matlab to graph and just kind of look at the graph. So let's go ahead and do that. Why don't we do an easy surf, and we're plotting the function f. Now, and this is actually the distance squared, right? So we could play with this from different points of view. Why don't we do an easy surf C? That would make it a little easier to identify visually where the minima is likely to be. So we need to zoom in a little bit, so let's do an easy surf C on F. And we're expecting the minimums at 2, 3/2. So why don't we make our X range maybe from 1 to 3, and our y range maybe from 2 to 3, and so I'm trying to think, kind of hard to tell which axis is which on the labeling here, but it doesn't look like, of course not, because the y value of the minimum is 3/2, and I didn't include 3/2 in the range. In other words, 3/2 is not between 2 and 3, 3/2 is between 1 and 2. So make that adjustment, and we should be able to inspect, and now we see that the minimum as expected is that x equals 2, y equals 3/2. So the graphing provides the nice visual assessment that we were hoping for.